So at this point, I'm going to turn it over to Sina, Semnani. Sina is the student who came up with so many ideas that we should do, and you will see what he has done. Okay. Well, thank you. Take it over.
I will talk about a few of the technologies that we have built, and I think the best way to demo them is to talk about History Genie, which is something that we have built that integrates a few of our technology, including search, semantic search, reliable chatbots, and literature search or STORM. So the motivation for that is that there are a lot of digitized archives everywhere. So this is from the Library of Congress, more than 21 million newspaper pages over the last over 200 years. And they have very varying degrees of difficulty for computers to process, very different layouts, a lot of images, a lot of maybe low quality images and scans, and all these make processing them for computers very challenging. Another example is the Colors Convention project. So it's from 1830 to 1899, and it's scattered throughout North America. And another example is the Markomo project, which has ship logs of French Mediterranean lines. And to give you guys a better an overview of how diverse these newspapers are, I've put a few of the pages from the Endangered Archives program here, and basically the map shows that any community that you can think of probably has a valuable resource that is not being accessed right now. So in History Genie, we try to apply some of our technologies to these corpora, to two of these corpora to begin with, and make them more accessible. So I think before I get into the technical details, we can go over a demo. So here I'm trying to browse the African Times, which is a newspaper published in the late 19th century. We have automatically digitized them, so going from scans to searchable text. And this is available in this format, so all the individual articles are extracted, the original images are there for users to view as well, and we can see them side by side, and we can always go back to the original source. So if you have attended yesterday's workshop, Professor Getz mentioned something about prohibition movement in Africa, in West Africa. And this is an article that I came across because I wanted to learn more about it yesterday. So it's someone writing this correspondence to the newspaper, and it got published in the newspaper, and it was reporting on the increase of the duty upon spirits imported into West African colonies. So it was proposing to do that. And the bishop maintains the present duty is entirely inadequate to meet the evil which the traffic caused and which is growing in an alarming rate. So this is like an example of someone advocating for limiting the import of alcohol into West Africa. Now that I have found something that interested me, I can go to Genie and search specifically for alcohol import in West Africa to see where else in the corpus it has been mentioned. And even if there is no exact keyword match with the articles, it can still find relevant documents for me to view. For example, here I find another article written by someone else. I should like here to revert to the liquor traffic in connection with the native races. And but if much higher duty were placed on spirits, gradually the demand would cease. So it's kind of in the same direction as the first person who wrote it. And this one was published in 1895, so the data is also automatically extracted using Genie. And after that, I can continue. There is a lot of search results on the same topic. And the interesting thing is that if I find something that is interesting, I can go back to the original page, the newspaper page that it has been extracted from, and actually see the original one side by side. Then the next step that I want to take to explore this corpus even further is I go to our chatbot, our reliable chatbot, and I ask why were import duties imposed on alcohol import to get a broader sense of the content from this corpus. It shows me the intermediate steps, what it looked for exactly, the ideas it came up with, and how it was doing the fact-checking process, which I will get to later. But the interesting thing is that it will give me a short answer with citations. So here I can go to, let's say, citation number 4, and this is the summary that it has used, automatically generated, and also the full text of the article from the newspaper, from the African Times. So there is something here about an individual opinionating about, so Sir Claude MacDonald sees no other means of raising the revenue present by a customs tariff upon the importation of trade spirits. So this person is seeing this as a means of increasing revenue for them by increasing tariffs. And I was reading this article and I saw, okay, there is this term I'm not familiar with, what is protectorate? So I can go back to the chatbot part and actually ask this question. And it will give me another side answer. Then I can go back to my original conversation and continue by asking, okay, all these were negative comments about alcohol. Are there any positive views? And Genie will come back with an answer and saying that, yes, actually, there are some instances in the corpus where the trader noted that drunkenness in West Africa was perceived to be less severe than in places like Liverpool, suggesting that education about responsible alcohol consumption could be more effective than prohibitive duties. And it was reported that the average consumption of spirits on the Gold Coast was nearly a gallon per head, yet this did not correlate with an increase in drunkenness. And also some believe that religious beliefs has kept alcohol consumption in check, basically, and there's no need for additional limits. And again, I can check the citations, and here I see that there is an article by Colonial Secretary Mr. Hudson. And again, I can go back and ask the chatbot about what this person was and what his role was, and it will tell me that was a colonial secretary. He expressed optimistic views and did not like to refer to African natives as hopeless people. So he was saying, okay, they have agencies, and now I can go back again to the original source, and if I want to, I can double check that it has been actually extracted correctly from the scanned documents all the way to the searchable text and the chatbot. So here is specifically where the chatbot took the code from. So my experience of him is that he is far from being the hopeless person so many people consider him to be. This is about the future of West African natives. So this is actually online. We have done 2 corpora so far. We are working on expanding it. And now there is another part on doing literature search. In this case, it is only using the African Times corpus, and it's 4,000 articles. And it actually generates, again, longer articles with citations this time, not just chat. That gives an overview about everything that has been discussed on this topic in the corpus. And there is a table of contents that I can read. And there is a list of references at the end of the document. And I can download it as PDF and use it as a starting point for my own research if I want to dig deeper into this topic. So next I will get into the technical details. So this is the 3 technologies that I was the four technologies that constitute history Genie. So let's say you have a corpus on the left-hand side. So the first thing that we need to do in order for any of our AI systems to work is to extract the text accurately. And then that would enable us to do semantic search on the corpus, as I showed you guys, and do reliable chatbots and writing articles. So my colleague Yu Chang will talk about the last part, but I will talk about the first three parts. So first of all, text extraction. So the question I had when I started this project was, is text extraction a solved problem, given all the recent advances in language models and in vision models and so forth? So it turns out that most academic data sets, especially, are focusing a lot on modern documents. So these are LaTeX files converted to PDFs, and their accuracy of text extraction on these documents is rather high. But if you get into like a scanned historical documents, things get complicated for these models. So let's zoom in on this example. So this is from the Library of Congress collection, I think, Chronicling America. This is one of the first reports on Titanic sinking. So it's early 20th century. So this is the zoomed in page, and we can read this. This is not blurry, not very low quality, and this is the text extracted by the system that the Library of Congress website is using. So a lot of things are right, and this is probably good enough for keyword search, although it does sometimes miss, like keywords like Titanic is misspelled sometimes. But it's the numbers are usually wrong, and you can't really use this in retrieval-augmented generation systems, or you can't fit it to LLMs to summarize or to draw insights from, or to use it in any other applications other than searching keywords and looking at the original documents yourself. So it's it helps a lot, but it's still not ready to be used for a lot of our other AI systems. So we wanted to see if it is actually the case where commercial systems can help. Maybe it's just that academic models are lagging behind. But so I gave this input image. So this is from the South African commercial advertiser. Has a relatively straightforward layout. So a header and 3 columns, not too difficult compared to some other newspapers. And this is from Transcribus. It's a commercial system. This is without fine tuning. The reds are errors, and the blues are omissions, and the greens are correct. So and this is Azure Document Intelligence, so it's a lot better. Here, I think a lot of the word levels are fine, even though it makes mistakes. The main problem is that the large chunks of text are shuffled around. So if you are trying to use an AI system to make sense of these documents at scale, it would basically be cut off mid-sentence all the time, and it doesn't really understand the narrative or the order of events or even the structure of single sentences because of that. And so we try to see if this can be improved given the recent advances in vision and language models. So usually, at least in the case for Transcribus and some other commercial systems, when you tell them that, okay, it didn't work on my newspaper, they say, okay, you can manually label some training data on your specific corpus, you train a model on that, or we train the model for you, and that will improve things a lot. That is probably true, but it's like, dependent on the layout and available manual labor, and it has to be done one newspaper at a time. And we thought maybe we can do this once and for all. So I looked into how maybe GPT-4o, which has a strong vision component as well, can help. And if you give it the same image as input, the outputs are kind of having a lot of problems. We can see that a lot of the large chunks of text are actually correct and they're green, but it still has the same issue with jumping around the articles in an incorrect order and cutting mid-sentence. That's kind of where the red section comes from. And also some relatively more local problems down at the word level or at the phrase level. But another observation is that if you actually give these large vision and language models small chunks instead of entire pages, for example, this is the same example as a few slides ago, they're actually really great at doing OCR, right? So the problem seems to be that large, complicated images are tricky for them, but small images, they are really accurate. And another example is, okay, this one is very, very hard to read. Even if I zoom in, this is actually the image is blurry in the original. I don't have a higher resolution. But GPT-4, kind of, I think it's mostly true. Like, I can look at them side by side and I can see that, yes, I actually agree with GPT-4. But I couldn't even make out some of the words myself without help. So another shocking thing that I didn't really expect it to be possible is they are actually really good at non-Latin scripts as well. So this is the first newspaper published in Iran. This is Farsi, read from right to left. And again, if you give a small chunk of the page, not the entire page, to GPT-4, it will be able to accurately extract the text. And if you ask it, it can also translate it to English. This is actually accurate translation. And so this is a very challenging setting. It's different scripts. This old style of writing. It's not really used as much anymore in this way of writing. But they still can tackle them. So the question is, what is it exactly that makes text extraction challenging when you want to do an entire page instead of small chunks? So if you look at what people typically do before large language models, is they have 4 different stages. The first one is pre-processing to just improve the quality of the image. Then they try to detect the bounding boxes. For example, here's a paragraph, here's an image, here's a title, and so on and so forth. And then for each bounding box, they run OCR on it, so they just extract the text. And then at the end, they try to figure out the correct reading order of the page. So for example, I first read the title, then the first column on the left, and the second column in the middle, and then so on and so forth on simple layouts. So the challenges and the limitations usually are that pre-processing step can be corpus specific. Different qualities of images, different conditions can require a little bit of manually verifying the pre-processing step. The layout detection, especially when you go from the modern PDFs that are easier to understand to historical corpora, becomes much more challenging for models, and their error rate goes up. There are still some OCR issues, even though I think that's a smaller part of the problem, that leads to words level errors. And reading order detection, as we saw earlier, can lead to models misunderstanding the flow of the narrative and even structures of sentences. So that's kind of like a more global type of error that usually happens. So we went back and revisited all these 4 stages and tried to see if large vision and language models can help. And so first of all, the pre-processing stage. So we've worked to make this a bit more general. So in the 2 corpora that we looked at, one of the challenges was that some images contain more than 1 page, and they have part of another page, sometimes written included as part of the text, but that is not meant to be, and things like that. So this step is actually very simple for vision and language models to figure out that there's multiple images here, and then we split the page if needed. And here is another example where there is a part of another page included, and it usually shows up in OCR results if you just run it through the models without any additional pre-processing. So what we do is we run a line detection system off-the-shelf model. So these are usually much more accurate than trying to figure out the bounding boxes. And then we automatically figure out what is outside of the main area with the help of LLMs. So we basically prompt GPT-4, see, okay, is this region part of the main page, yes or no, and we remove them to make the next steps easier. Then, for the second stage, we run OCR on each line. Again, here OCR is replaced by a simple prompt with GPT-4 that we give a slice of the image as input, and we ask it to generate the text content of that. So far we have, about 700 in this example lines, and we have extracted their text. But now the question is, what order should they be read in, so that we can concatenate the strings that we got from each line and get the full flow of the text and flow of the content. And this turns out to be the most challenging part. So now visually, we can of course see that there are multiple columns, but in general, that's not the case. Especially historical newspapers can have odd and unusual layouts where content gets cut off mid-column, and there are horizontal columns, and images in the middle can be embedded, and so on and so forth. And the way prior work usually tries to tackle this is that they take a top-to-bottom approach. So they first try to figure out the entire structure of the page. So for example, given the whole image, try to figure out where the columns are, and try to process the entire image at once, and then after that try to find the reading order. But what we do, and what we found out to be more suitable for large language models, is that we can do a bottom-up approach. So we first start with lines and try to reconstruct the hierarchy of the page from the lines. The key difference here is that if you want to merge at a line level and try to move up from there, you only need to make local decisions at a time. And it turns out that in practice, making local decisions is much easier for neural models in this setting than trying to process the entire image at once and trying to figure out the flow of the text that way, the way prior work used to do. So now the question is, let's say in this example has hundreds of lines, how can we find the correct order of all of them? So here is basically the final version of the algorithm we are using. This is still work in progress. It does work really well on the examples that I've showed you so far, but there are still challenging cases that we're trying to work through. But I think so far, even though it's not completely finished, it's much better than existing work. So we're really excited about that. The way the reading order parts of this works is, well, I need to first define a few things. So the problem can be easily translated to a graph problem. Let's say every node in the graph is one line from the document, and the task is to basically find a sequence of nodes. Let's say you start from the title, and title is a node, and then you move on to the first paragraph of the first column, that is node 2. And the task is to basically find this reading order graph, which is basically just a line. And a naive way of doing that with large vision and language model is, I can look at every possible pair of lines, and I can ask LLM, hey, do these two lines seem to be next to each other in the reading order of the page? And it's a binary classification task, and the answer is yes or no. The problem is it will take n squared LLM calls. But in principle, this will give you the correct answer given your LLM is accurate enough. So how can we make this actually tractable? So first of all, there is a lot of things we can deduce from the geometry of the page. For example, if I'm at the end of a page, at the bottom of a column, it's very unlikely for the next text to read to go upwards or up and left if it's a left-to-right script. So we can use this geometry and to reduce the size of possible pairs that we have to look at. So let's say now we have 10 times fewer edges to look at. So that's one source of optimization for making this work. And another high-level idea is that the correct reading order of a newspaper page is such that it minimizes having to jump around a lot. So basically, if you're reading a piece of text in a page, it is more likely for the next piece of text to be close to it than for it to jump around on the other side. The exception is at the end of the column, but if we consider the distance to wrap around the page, so the bottom of the page and the top of the page are basically the same point, then that would take care of that problem as well. And the way we try to impose this structure on the system is we solve this graph problem where we find the path in the graph that goes through all the lines once and minimizes the amount of distance you have to jump from one point to the other. And there are approximate solvers for that, and we are using them, even though the main problem is NP hard. And then, after all these steps, we can run this algorithm. It basically iteratively tries to remove the edges that are clearly, according to the LLM, are clearly not adjacent in the reading order, and get down to just a single line going through all the nodes. And this is n log n instead of n squared, so it's much more efficient. It's actually feasible to run with LLMs. I think the visualization can help a lot. So this is where we start from, and we are trying to figure out, iteratively, which lines are read together. And at each point, when we merge bounding boxes, we know the order. We have already figured out the order within that bounding box because that's how the algorithm works. So in this example, basically after 11 iterations, the entire page has been scanned. And so for example, this means that by the iteration 10, it has figured out that this page has 4 columns, even though there was never an explicit mention of it anywhere in the algorithm. And iteration 11 is where everything is finished and we have the final reading order of the page. So in a more complex layout, let's say there are no well-defined columns, this gets a bit more tricky. It still works in general, it's just that the accuracy is a bit lower and we're working on that. So this is an example of a more challenging case where you have to read from top to bottom, then you move to the text above the image, and after that you have to kind of move diagonally and read it here. So this is a more challenging case. In the same page, there's another place where you have to read top to bottom and then move here and read the screen part, and then move up and read this part. So basically we are trying to handle all these cases without having to manually either label data specifically for this layout or write additional code to impose some restrictions. And we are not quite there yet in this complicated case, but we are trying to move towards it. So right now, History Genie can extract individual articles in this page, but the global order still has issues. On the simpler case on the African Times, that automatically works, and the accuracy is quite high because of its relatively simpler layout. And making it work in practice had some challenges. One of them was that at a step in the algorithm, we were asking a language model to make a decision whether 2 pieces of text in a page should be read right after each other or not. So there is an error case there, and we try to get around that by basically cutting different views of the page, different subsections of it, and asking the same question from different angles. And combining the answers in that way increases the accuracy, it seems. So this is an ongoing project, and we're working towards a publication. But I think the initial results are interesting, as I showed you guys in the demo as well. It is useful and highly accurate for moderately difficult layouts. The cost right now is 50 cents per page. It is LLM cost. And LLMs get cheaper and cheaper. So next year it's going to be probably 10 times cheaper. So now that we have extracted accurate text, hopefully the global order is correct and the words are much better than commercial systems at the word level as well. We want to make it possible for people to search through this corpus and also enable RAG applications and chat applications that rely on search. So just a very quick overview of what information retrieval does under the hood. Basically, we have a search query. It can be a sentence, can be a question, can be a phrase. And we want to get the most relevant results and results from the corpus that we have. And what Retriever does is efficiently looks through all possible newspaper articles, for example, in the case of African Times, if it's Wikipedia articles, and finds the most relevant ones in a very efficient manner. This is usually done by a vector search. So, we are using the state-of-the-art multilingual vector model. So it supports 70 languages, and we have put out a very efficient deployment of it for our other projects, and I will show you guys a link to request addition of your corpus as well if you're interested in doing that afterwards. But usually these systems, even though it is a strong retriever, has challenges with finding relevant information when it comes to either time-sensitive information, like you want the latest one, or you want something to be at a specific date, or working with specific named entities, especially if they are lesser known. So for that, it turns out that we can actually use a large language model again to more closely score the relevance of each retrieved document with the original user query. So for example, in this case, the first one, the scores are between 0 and 1, and some of them might not be relevant, might be closer to 0. And this way, doing this in this way, because of the deeper understanding that large language models have of language compared to just embedding models, it improves the accuracy of search results a lot more. So we have a hosted version of Wikipedia and Semantic Scholar. So it's a free API for researchers to use if they want to, but also we have this option of adding new documents. So now we have been able to extract text and search through it. And we use large language models for both to improve text extraction and improve finding the most relevant things to what the user is asking for. But there are a lot of applications where you actually want to explore not just what you're specifically asking for, which is what search does, but you want to get an overview, a broader thing, a broader understanding of the concept. And that's where chatbots are really, really helpful. The problem is usually they hallucinate. So if it's a search interface, you can just read the original document, and there is nothing between you and the information, so there is not a chance for it to change. But when you use chatbots, there is they are kind of sitting between you and the information, and there is also this problem of can you trust them or not? And we started by really asking the question, what applications it could enable if you had a reliable chatbot. So, first of all, it would be very much easier to use as an end user, but an interesting application of it was, I think Professor Gates mentioned it yesterday, was it makes it more possible to use these things in settings like classrooms and potentially applications like journalism and so on and so forth that really rely on highly accurate processing of information in order to be even useful. And in the rest of the talk, I will talk about this specific paper called WikiChat. Originally was mainly focusing on Wikipedia because of its scale, but we have expanded it to other corpora as well, as you saw in the demo at the beginning. And right now it has support for 25 languages from Wikipedia, and achieved in our test a 97% accuracy when talking to users about recent events. So these are events that the underlying language model has never seen. But using WikiChat, it's actually able to be very highly factual when talking about them. Another use case of reliable chatbot, especially with multilingual, is that it can pull the world knowledge from different languages and different corpora that might not be accessible to an individual person and make them accessible. So here's an example where there is a piece of information in the Japanese Wikipedia, actually, about a Persian physician that the English Wikipedia is missing. So it's kind of a combination of, you would expect it, either the Persian one or the English one to be more complete, but it just happens that there's a Japanese article that is more complete on the same person. And making these connections without automated tools is very difficult, but if you're using a multilingual chatbot, it becomes very natural. So for the rest of the talk, I will be mainly using Wikipedia as an example, even though the method is very general. And we start with Wikipedia mainly because its size and multilinguality means that if you can build something that works with Wikipedia, it's likely to transfer. And later on, we showed that it actually is true in the case of this WikiChat. And another thing is the breadth of topics. So it's not necessarily specific to a domain. Anything that Wikipedia covers, this chatbot can handle. So usually when people want to mitigate hallucination of large language models or give it access to information that it hasn't seen during training, let's say a historical corpora that has been digitized recently, or the news that's came out in the last few months and hasn't been trained with, or even older knowledge, people use this thing called RAG, which in the most simple case and the most common case is, given the user's query, they search the knowledge corpus, in this case Wikipedia. This example, we ran this example before the movie came out, so it's quite old. But at the time, it was new knowledge for the model. And then they get a bunch of top results from the retrieval stage, and they give that to another language model to generate the final response to the user. The problem is, even though they are supposed to access information from the corpus, in practice, they still hallucinate. So there was a study from Stanford that evaluated these commercial chatbots in 2023 and said that even though they cite things, the citations are not accurate, and a lot of the times they should be citing things, but they don't. So that's the low recall, meaning that they are making things up without citing them. And this is an example that I could find from chatting with Perplexity. I think they have fixed it since then. But my advisor, Michael Lamb, brings up John Hennessy a lot. And so I was wondering if he was Michael's advisor. And yeah, I mean, Perplexity says yes, even though, Monica was at CMU and has nothing to do with Stanford at the time that she was studying her PhD. So I know now that it is false, but could have gone very, very wrong. So the way we try to tackle this problem is basically we break down the task of accessing knowledge into very, very simple atomic steps. So after we evaluated why RAG systems still make these mistakes and hallucinate, we found out that the problem can be solved by breaking down the tasks that they're trying to do in one step into multiple simpler steps and making sure those steps are fine. So the overview is the overview of the WikiChat system is that given a user conversation, the history of the conversation, we search Wikipedia with one or more queries, and then we filter out relevant information. So that is one new part I will talk about in more details. In parallel, we also want to still access the vast knowledge that LLMs have and the way they can give you relevant and interesting information. So we also ask the LLM for the answer. But we know that it can't be taken at face value, so we meticulously and automatically fact check each claim that it makes using, again, information from the corpus. And we remove the incorrect claims that don't add up according to the corpus. And finally, we draft the response and refine it. So again, multiple easy LLM steps to consult external data instead of trying to do everything at once. So the first limitation that we identified in RAG systems was the case when retrieval results contains what the user asked for, but also similar sounding related, but irrelevant information. So here, I was asking this state-of-the-art RAG system at a time about books and the movies that have been made from them. And the retrieval result returns this novel, but the generation part of Retrieval-Generated thinks that it is actually a movie, and it goes on, and based on that, it kind of goes off the track very quickly. So what we did, so the first part is the usual RAG. We added this summarization and filter step. So we separately, before we even attempt to generate an answer, we have another specific stage to get rid of all these distracting information, especially with respect to similar sounding entities or long inputs. And the effect that this has is that it makes the job of the next step, which is writing the final response, much, much easier. Then we don't have to worry about these distractors. We identified that another source of limitation in this case is not necessarily hallucination, is that if you just rely on RAG systems, you lose some of that, what I call LLM magic, that if you just remember how it felt for the first time to talk to ChatGPT, was, you ask it something very simple and it doesn't just answer what you asked for, but also is able to understand what you're interested in some ways, and give you very natural and very relevant information without repeating itself. And this is something that at the time especially, and even to this day, RAG systems fall behind compared to LLMs. So we wanted to try to add this back into WikiChat, and for that we added another route, as I mentioned earlier, to directly generate responses from GPT-4 or any other LLM that we're using. So in this case, you can see that LLM is coming up with this idea that Christopher Nolan is known for his meticulous casting choices, which was not directly found from the retrieval because it's not really related directly to what the user asked. But it's very interesting, right? But also on the other hand, it came up with some hallucinations in red, like Tom Hanks starring in the movie Oppenheimer, which is completely not true. But we were able to fact check that again using another LLM call and retrieving more information from retrieval, from Wikipedia in this case, and just keep the good parts and get rid of the bad parts. So in this way, we can get access to information that was very difficult to directly retrieve, but because the LLM is kind of bringing that up, we can get access to that. And then finally, we write a draft and then separately refine it. And the reason is we added some constraints on what the draft stage can do. It cannot make up new things. We have separated what's the part where we want the language to be natural and engaging to the user to a separate stage, so that draft can focus on being factual and saying I don't know if it's necessary. And in this case, it is basically putting things together, the draft stage. And then the refined stage can come in and say, add engagement if needed. For example, I'm sure it will be an excellent film. Like doesn't have additional factual content, but sometimes helps with how the responses are perceived by the user. So I mentioned that basically we have two routes. One is directly retrieving information, which RAG usually does, but the other one was generating a response from LLM and then fact-checking it. So this is an example that shows how these two kind of add to the final response, and one of them at a time would be missing something that we could otherwise have. Here, for example, I'm asking about Sting the musician, and WikiChat, using retrieval in this case, comes up with a very standard background on the musician from Wikipedia. And then I'm asking like a bit of a more maybe opinion-oriented question, but it requires a lot of facts to be, based on something. And that is where actually LLM-generated content after fact-checking becomes very useful. So here it says he often uses his music to express his own thoughts and feelings. That's probably always true for all musicians. But the ability to blend different genres, that is actually verified against the Wikipedia article, and we know that's true because it's been mentioned in different genres, for example. And in the last response, there is this the fact that it needs to know or mention his birthplace comes from LLM, but the specifics of this anecdote of Queen waving him from a Rolls Royce is retrieved. So it's basically you get the facts from the corpus, but also you get all the fact-checked engaging parts from the LLM, the best of both worlds. The third limitation that we identified was RAG system hallucinates when retrieval results contain no relevant information. So here we expect the chatbot to say, I don't know, but in practice, the LLM usually makes something up. And that goes back to the low recall of citations in the study that I mentioned earlier. So that a lot of things don't actually have citations. In WikiChat, on the other hand, the stages and the separation of tasks has been designed to specifically, first of all, filter out the things that are not relevant. Therefore, if there is no relevant information in the retrieved results, the output of the filter will be empty. And so we impose this explicit constraint on a draft stage that it has to say, I don't know if that set is empty. And finally, the refined stage is allowed to sugarcoat the answer and say, I'm sorry, I couldn't find any movies based on what you asked for or whatever the context of the conversation is, but it doesn't add any new information. So I will briefly talk about how we evaluated the factuality, and it turns out to be actually a bit more, need a bit more care than it seems on the surface. So the first observation is that LLM's hallucinations are dependent on the topic. So if you ask who directed the Godfather movie, that's a very well-known fact. They will get it right most of the time, at least the recent LLMs all do. If I ask about a lesser-known entity, or a tail entity as we call it, more likely to make mistakes, and so the factuality goes down. If I ask about something it has never seen during pre-training, like a recent thing that happened, it will be even less accurate. Now, the problem is that most interesting use cases like medical, legal, historical, and corporate falls into the last category. So that's one of the reasons we think that LLMs sometimes seem like they're very, very factual when tested on certain types of knowledge, but if you actually want to use them in certain applications, it becomes very, very hard to trust them and rely on them. And this actually, I think, has affected negatively how people have been evaluating chatbots, especially in the beginning of the LLM era. So, most people in academia used, and still do, use static benchmarks that are crowdsourced. So a property of these benchmarks is that people are asked to talk to the chatbot, and people usually choose to ask about what is familiar to them, which means a lot of these benchmarks don't include tail knowledge or lesser known knowledge or technical knowledge. And the other thing is that if you use static benchmarks that have been collected and as a standard as part of research to collect, they're missing the recent information. So we never test them on test models on recent information. So instead of these, we propose to do a simulation-based conversation where we specifically ask a user simulator to talk to a chatbot about hard topics, about recent topics, about tail topics. And finally, we evaluate them with a user study with real people to just make sure that it translates to the real conversations. And there is a whole protocol for how we evaluate the factuality. And I want to emphasize that this cannot be done fully automatically. We can use automation to help with steps, but it's kind of like not really possible to test the factuality of the best models using themselves. Like you might be able to test the capabilities of a weaker model using a stronger model, but it's really human evaluation. And careful human evaluation is probably the best way of doing fact-checking at the end of the day. So here are the evaluation results on WikiChat. So, again, the test is broken down into head topics, tail topics, and recent topics. And as you can see, GPT-4 is really good at head, like 94.9%. But when you get to recent conversations, it goes below 50%. And Atlas is another, at the time, state-of-the-art RAG model, which performs reasonably well, but it still has a bit of a drop. And this is WikiChat based on GPT-4. So WikiChat, where each stage is implemented using a GPT-4 prompt, and improves the accuracy over GPT-4 a lot, especially on tail and recent topics, and on average gets an accuracy of 97.3% on our tests in terms of factuality. And as I said, we wanted to validate this and make sure that this translates to real users. And so we conducted this user study, and WikiChat got better user ratings overall. But the interesting part is that the factuality was actually more than doubled in conversations with about recent topics with users. The tricky part is that we also collected comments from users after they talked to these systems. And most of them were not even aware that what they have heard from GPT-4 is actually untrue, because it was very convincing. So, it makes it a bit more important, in my opinion, that we are able to have reliable chatbots because we're really good, it seems, at deceiving and seeming truthful even when they are not. So I want to spend a couple of minutes talking about the implications for cost, privacy, and latency. So I mentioned that we have this more elaborate way of doing RAG with WikiChat for the sake of improving accuracy and factuality, but it does have some downsides. For example, the cost, because we're making more LLM calls in this case, and the latency goes up a lot. So also you need to send your data to LLM providers, which is not really desirable for a lot of applications. So what we did, again, in the paper, there's more details if you're interested, but the general idea is that we generate a lot of conversations, a few thousand conversations, with WikiChat based on, let's say, GPT-4 as a teacher model. And we record its inputs and outputs for each stage of the pipeline that I showed you guys. And we store that and we use it as supervision to fine-tune a smaller model, in this case, the Llama 7 billion parameter model. And at test time, we run that smaller model instead of the teacher model. So it's cheaper, lower latency, and also it can be run locally. And the results are that actually it becomes comparable in terms of latency to using GPT-4 out of the box. So this was done a while ago. Now that the numbers are different, but the relationship is the same. And it's cost as much as your local GPU or even CPU costs. And it is as fast and much more accurate. So in terms of accuracy, we do see a little bit of drop in terms of this process of switching from GPT-4, let's say, to Llama model by about 6% on average, but it is still much better than the base GPT-4. It's kind of similar to GPT 3.5, WikiChat based on that. So basically, the process of distillation brings us down by a few percent in terms of accuracy, but it's still better than the baselines. And as I mentioned earlier, we wanted to also make sure that our RAG system is still comparable to that magic that LLMs have, which were they give you relevant results and very informational and natural responses. And these are out of 5, and on average, it is, even though slightly lower on certain aspects, but it's much better than other RAGs, which is so the Atlas, the green bar. Especially a lot of the times it gives you irrelevant information, so that's scoring very low. But WikiChat is scoring close to base GPT-4 in that aspect as well. So there is a demo, and the history Genie is there. WikiChat on different corpora is there, and you can also check out the code if you're interested to run this locally or learn more about it.